Assalamu alaikum. I am Nusrat Jahan Meme, ID 251160445, batch initial 21B, Department of Computing and Information System, Daffodil International University. Today, I will be presenting our project on instruction set designed for real-time health data for the course Computer in Architecture and Organization. Before we start, let me briefly set the stage. In today's world, healthcare data is generated at an incredible rate from hospitals, clinics, and even wearable devices. Managing all this information in real time is challenging. Our assignment focuses on designing a smart computer system that can handle this challenge, processing massive streams of patient data quickly, reliably, and efficiently. The scenario focuses on building a smart computer system for a national healthcare data platform that can process massive streams of patient data in real time. In this system, speed and reliability are not just nice to have, they are essential. Imagine a hospital emergency room sending patient vitals to a center this database every second. If the system lags, doctors might see outdated data, which could be dangerous. Our goals are threefold: efficient instruction execution, fault tolerant memory handling, high throughput I/O. Each team member worked on a different part. Some focused on designing a RISC instruction set that is simple and fast, others on an advanced cache system to reduce data access time, and others on virtual memory, I/O systems, parallel processing, pipelining, and the control unit that coordinates everything. Task 1 is about understanding the basic structure of a modern computer system. The CPU executes instructions, memory stores data, I/O units handle communication, and buses connect everything. The CPU is the brain. It fetches, decodes, and executes instructions. Memory stores both of the program, instructions, and the data. I/O units are like system senses and hands. They send data out and bring new data in. Buses are the highways that connect all these components. We also discussed memory hierarchy, the idea that not all memory is equal. At the top, we have registers, teeny, extremely fast storage spaces inside the CPU. Next is cache, then RAM, then finally hard disks or SSDs, which are slowest but store the most data. In our design, Ms. Nabila implemented a two-way set associative cache. This groups memory addresses into sets and allows faster access by keeping frequently used data to closer the CPU. Lastly, we explore RISC instruction formats and their addressing modes. Immediate, direct, indirect, register. Like immediate, the value is part of the instruction itself. Direct, the instruction contains the memory address. Indirect, the instruction points to an address which then leads to the data. In register, data is accessed directly from the CPU register. In task 2, we showcase 4 sample instructions from a custom ISA, each using a different addressing modes. This example helps us to see how different addressing modes work in practice. For example, using immediate mode for constants avoid extra memory access, making execution faster. For the cache, our two-way set associative design uses the leastly recently used LRU replacement. This means when the cache is full, it removes the data that has not been used to the longest time, similar to clearing out old files from your disk to map space for new ones you use often. In virtual memory, we implemented paging. Memory is divided into fixed size pages and mapped into physical frames through a page table. This allows programs to run even if the data is not all loaded into RAM at once, which is critical for handling very large datasets. Using optimized replacement is algorithm reduce page faults. Situations where the system needs to fetch data from disk, but because it's not the memory. Task 3 focuses on the pipeline and parallel processing. We used 4-stage pipeline: fetch, decode, execute, and write. Pipelining means multiple instructions can be in different stages at the same time, like an assembly line. But hazards don't occur, can occur. For example, a data hazard if one instruction depends on the result of another that hasn't finished yet, or a control hazard if a branch instructions change the flow unexpectedly. In conclusion, this system design combines a risk-based ISA, advancing caching, virtual memory management, memory mapped or IO, pipelining, and parallelism to deliver a high performance and fault tolerant platform for real time healthcare data processing. Thank you.